So today, 4.4 is about a thing called asymptotes, which you've seen a little bit of algebra 2 days, and a thing called dominant terms that you've never heard of until this moment. Remember what asymptotes were in algebra 2 at all?
It had to do with graphs.
It did have to do with
I
graphs.
was thinking lines that it couldn't go past.
That's correct. It was like a line that you couldn't touch. A little bit that happened in trig also. Algebra 2, you guys had this in quarantine, I believe, where there was a thing where we graphed like a box like that, and then diagonally we drew these lines through the corners of the box, and eventually we ended up with a graph of a thing called a hyperbola, like this, that had to not cross those diagonal lines. Those diagonal lines were called asymptotes. That's probably long gone from your memory, because anything we did in quarantine is probably just erased. But that was like at the height of COVID, one of the things that we were doing. You might more likely remember from trig, we did some trig graphs where we had a sad face graph where there were asymptotes here that we weren't touching. The tan graph had asymptotes we weren't touching. But we've seen asymptotes before, a little bit, here and there. They're just lines on a graph that you're not supposed to touch. You're not supposed to cross them, not supposed to touch them. They kind of create some boundaries for us. So in this lesson, and this is more algebra-ish than calculus-ish, you won't do the derivative today at all. So I'm not sure why this is in the derivative chapter, because there's nothing really to do with derivatives in this today. But we're going to find 3 types of asymptotes. There can be horizontal asymptotes, so that would be like a horizontal line that you're not touching. This touches on calculus, and this is the only thing that really touches on calculus, because to do those horizontal asymptotes, you have to find limits as x approaches infinity from chapter 2. We had rules about that, and I'll let that just stew for a minute, and we'll come back to that. Vertical asymptotes you're going to be better at. Okay, vertical asymptotes, you just look at the bottom. If the bottom equals 0, you would have a vertical asymptote, a vertical line that is untouchable. Then there's another one called an oblique or a slant asymptote. I prefer the title slant asymptote, so that's what I'm going to use. The slants, we can only find them if the top of a fraction is 1 degree higher than the bottom. You know what I mean by 1 degree higher? What's that mean when I'm talking about the degrees of polynomial stuff? The power, the highest power. So if the top is 1 power on the variable higher than the bottom, what we'll do is long divide to figure out what the quotient is. Slant asymptotes go diagonally. So there will be some horizontals, some vertical, some diagonals. You don't maybe have all 3 of those all the time, but like all 3 of those are possible to exist. Asymptotes can go vertically, horizontally, and diagonally. Let's go back to this question. If we're looking at fraction things, and the board out over here is full of fraction things, how do we find the limits as x approached infinity? Remember that rule from chapter 2? It was a rule in 3 parts.
The bottom can never be higher degree than the top, or else it's 0.
So if the bottom had a higher degree, you'd go with 0. That's true. And there's none like that on the board, but there are some like that in the homework, where if the bottom has a higher degree, we go with 0.
And if the top's a higher degree, is infinity.
It is. And for today, we're not going to do that. Okay, we're not going to do infinite asymptotes. If the top has a higher degree, we just won't find the horizontal. What if they tie?
Fraction.
Then make a fraction. And we do have some of those, both on the board and in the homework. I'll come back to the question, can a problem have all 3 types? So we'll do a few, and then we'll come back to the question, could we go 3 for 3 and have it last? Question about any of that before I stroll right to a problem? So for this one, would we have a horizontal asymptote? No. What? Top is bigger. Top is bigger. That would lead us to infinity. We're not doing that. Would we have a vertical asymptote? Yes. What number would cause the vertical asymptote? -9, because -9 would make the bottom 0, and that's how we find our vertical asymptotes. Would we have a slant asymptote?
Yes.
Yes. What are we going to have to do to find it? Divide. So you have two choices for division. So one choice, if you're more comfortable with it, is long divide style. X plus 9 goes out. X squared plus 5x plus 7 goes in. And just divide the leaders. If we divide the leader of each group, that gets us x, gets us, and then as always for dividing, we subtract -4x, and now we redivide the new leaders. -4 gets me, and I should have probably dropped the +7 down just to have that be a little more convenient. Remainder, +43. We go minus minus makes a plus on that. We'll write the remainder as a fraction. But only the quotient matters for the slant. The slant asymptote would be x minus 4. Question about that?
Do you have to do it that way?
No. Alternative plan. Anytime it's an x, a plain old x, we can do a thing called synthetic division. If there's a x plus 9, we're going to put a -9 into the box, the square cornered box. And we did this in quarantine of algebra 2, so this might have been the best too hard. And then we only have to copy the coefficients, 1, 5, 7. We draw a little square corner box in the opposing corner. That's where the remainder is going to live in a minute. This was called synthetic division. Do you remember how this process commences? We drop the 1. Bottom level times what's in the square makes -9. Add those together. That's -4. And then what did I say for bottom level? Times what's in the box is 36. And then add down. That's 43. If you look at this compared to this, you'll notice we just did all the same numbers basically. Like, there was a -4, there's a 7, there's a 36, there's a 43, there's a 1 and a 4, like it all appears. Since this started with x squared, this just goes down a level of x's, so that's an x. That would have to be a number. That would have to be the remainder. I'm more of a fan of that, but you can only do that if the divisor is like a plain old x. If this is an x squared, you can't do it. If this is like a 10x, you can't do it. It has to just be an x that's leading the way on the bottom. Question about that? So that didn't have all three, so that's my question. Can we have all three? We'll figure it out in a second. New problem. Horizontal. Yes, it would be tie, so what fraction? 2/5. Since the x squared's tie, make a fraction out of the coefficients, the 2/5. Vertical? No, can't do it. There's no way to make the bottom 0 there. Slant?
Also no.
Also no. The slant is very picky. The top has to specifically be 1 power higher than the bottom. So with an x squared on the bottom, unless this has an x cubed for its champ, the slant is the least likely thing you're going to find in this homework. Question about that? So then let's ask the question, again, we did not find all 3. Do problems exist that would have all 3? No. Why?
Because
Which ones can't go together?
1 and 3.
Why?
Because if the top is bigger, then they can't be a tie or the bottom being bigger. So they
Yeah.
can't.
To have a slant, you need the top to be bigger by 1. And if the top is bigger at all, we don't have a horizontal. So you can never have both a horizontal and a slant. You might have neither one. You might have one, but you'll never have both horizontal and slant. It can't happen. You'll always get at least one no answer out of it, and that speeds our life along a little bit. That's never a bad thing, in my opinion. Question about asymptote lists? Let's add on another item then. There's going to be 2 dominant terms. Okay, to figure out what the dominant terms are, we're going to have to divide it, be it by synthetic division or be it by the normal standard long division process. Whatever quotient we get is going to be the dominant term for large x's. Whatever remainder we get, if we write it as a fraction, that'll be our dominant term for small x's. So let's go back over here where we came from. We'll add those on. We already divided this one. The dominant term for large x's would be the x minus 4 that we already obtained for the quotient. The dominant term for small x's would be the fraction 43 on top of x plus 9. And you don't understand what that means. I'll explain what the dominant terms mean in a second when we do the last example. The last example will give it some meaning. For now, let's just find them, and then we'll make them mean something in a minute. How would we find the dominant terms off of this? What do we have to do that we didn't do yet? No. What's the key to getting the dominant terms? We've got to divide. So this one we had already divided. This one we're going to have to divide to figure it out. So 5x squared plus 1 goes out. 2x squared plus 3x plus 4 goes in. And this is an awkward one. Whoop. Right in the wrong spot. 2x squared plus 3x plus 4 goes in, I say, as I write it in the wrong spot. Bottom goes out, top goes in. If we divide the liters, what would that turn up to be?
2/5.
2/5. If we do this divided by this, the x squareds would cancel, we get 2/5. If you distribute the 2/5, you get a 2x squared, that's why we picked it, plus 2/5. Remainder? 18/5 is fine. So the large dominant term would be 2/5. The small dominant term?
3x plus the 18/5.
3x plus the 18/5, but not all by itself, over the original 5x squared plus 1. And then that probably annoys most people in the math community because you're not really supposed to have fractions inside of fractions. I don't think that's super likely to happen a lot in the homework, so I don't want to overdo this. Usually it'll work a little cleaner than that. But if we do want to fix fractions in fractions, since this is over 5, we'd want to multiply everything by 5. So the 3 could be a 15. The 1 could be a 5. The 5 could be a 25. That's a better answer. Okay, is that a likelihood? I mean, it may happen here or there. You get a fraction and a fraction, but I don't think that's like a dominant thing. And we've done that before in algebra 2. The other thing you keep an eye on is if you can divide everything by something, you would. So if this were like a 10, I could divide them all by 5. Likelihood of that, probably low. You know, if everything had an x, peel an x off of everything. Likelihood of that, also low. Question over there. So let's do another one. So, horizontal. No. Vertical.
Yes.
9. Slant.
No.
No, because top's not bigger by 1. And then to figure out the dominant terms, we're going to have to divide. I would not long divide. I would synthetic divide at every opportunity. Does this work for synthetic divide? Yes, because the bottom has a lonely little x. No numbers, no powers, no nothing, lonely little x. So who goes in the bonds? Positive 9. And then what's a little bit tricky about the coefficients this time?
I usually leave gaps.
We have to leave gaps. We're actually going to fill in a number though.
1,
So there's 1 for x to the 4th,
0 for
0 x cubes,
0 x,
0 x squared,
0 x,
0 x's,
7.
and that's 7. And I may not have made myself enough horizontal space. If you have more horizontal space, I might make those gaps a little bit wider than what I did. How's the process start? Drop the 1
9.
times 9.
Drop the 9.
Add down
81.
times 9 is 81.
Drop down.
Add down is 81
729.
times 9 is 729.
Drop down.
Add down is 729.
542.
It's got to end in a 1. 65, 61 maybe?
Yeah.
And then
Plus the 7.
plus the 7, so 65, 68. Oof. They don't usually get that big, but synthetic dividing was a lot nicer than regular dividing, I'll say that. So the large dominant term, since this was an x to the 4 problem, this is now an x to the 3rd type answer. So it would be x to the 3rd
Plus 9.
9 squared, 1x,
Plus 7.
729. The dominant small
6, 5, 6, 8.
over the x minus 9.
Okay.
Just keep the original bottom. Something there. One last tidbit. We're going to graph some of these. I'm not going to graph any of those. The only way we're going to find graphing that would be very helpful is if the dominant terms were graphable, and we have no idea what this would look like. So this dominant terms would not help us graph this one. We didn't get much information out of this, so that wouldn't be very helpful to graph. This one wouldn't be so bad to graph using the dominant terms. It'll be a little similar to this one, but I'm not going to go back and do that one either. But if they ask you to graph using dominant terms and asymptotes, just kind of like make the list. Horizontal, vertical, slant, large, small. Horizontal. No. Vertical.
Yes.
namely 0. Slant?
Yeah.
Yes, in a second we'll have to divide. And divide the large and small anyway, we're going to have to divide. Here's a different kind of division. Okay, so we did a couple by long, 1 by long division, 2 by long division. We did 2 by synthetic division, so we did the one problem 2 ways. We can do a different kind of division on this. If there's only a single item on the bottom, what can we do for our division? Just separate it into 2 fractions. The quotient will be obvious because it won't be a fraction. And the remainder will be obvious because it will still be a fraction. So if we separate that into 2, what's the non-fraction part of it? That's the x. That's both the slant and the large. And then what would the small be that is a fraction? Whatever x. Question about list making. For everything, we're going to do the list making. That's going to be every problem in the homework list make all the way through horizontal, vertical, slant, large, small, do them all. Then for the 3's, I believe it's just for the 3's themselves, we are going to graph. So a vertical asymptote at 0, I'm not going to graph that, but I'll just let you know the y-axis itself is going to act like an asymptote. So when we graph in a second, we are not going to touch the y-axis. A slant asymptote of x, imagine graphing the line y equals x. How does the line y equals x get graphed? What's that do for us? You won't need graph paper or something, we're just doing sketch graphs. Y equals x, how to graph?
Just a diagonal line through the, like going from the bottom left to the bottom.
Yeah, it goes through the origin. So through the origin, and it splits these quadrants dead in half. Let's take a small stroll back over to the left for just a minute. If we did want to graph this x minus 4 graph, how would that have gone? Down 4 to do the y-intercept. And then with the slope of 1, you'd go up 1 over 1. We could get some stuff like that. What if this were 2x minus 4? Up 2 over 1. What if it was 2/3? Up 2 over 3. What if it was negative 2/3?
Down 2 over 3?
And so on and so forth. Okay, so we are going to have to graph some lines in this. The slant asymptotes will always be lines, and we can just graph them with like our y equals mx plus b kind of skills. If this is the dominant term for large x's, what I'll do is just put some gentle stars at the farthest ends of that graph. Because what this means is, as the graph gets way, way out to the right, it's going to get really, really close to this. It's never going to touch that because that's an asymptote. We're not supposed to touch. But if we go out and out and out and out, the graph we're about to graph is going to get closer and closer and closer to that asymptote to a point where it might as well just be on it. That's going to happen to the large dominant terms when you go to the extremes. Way to the right end, way to the left end. That's like targets we want to be getting near but not touch, if that makes sense. The dominant term large are called that because large x's live to the farthest ends of the earth. The small dominant term would be a graph that we're going to resemble when we get in tighter to the asymptotes, in tighter to the origin, in tighter somewhere in the middle. Do you remember what y equals 1 over x looks like? Probably not. Usually ask. It's going to fill first and third quadrants like that. That is a graph you want to get in your notes. What if I squared stuff? How does squaring always change things in math? No, if it's regular squares, yeah, but not fraction squares. No, it won't be a u. But squaring makes everything possibly bigger, positive for sure. So if we had the same kind of graph, but couldn't have things go into negative count, thought on what that might look like, and you'll want this one in your notes as well.
The negative part is screwed up.
Scoot up or flip up?
Flip up.
Flip up. So it's going to look like a funnel, like an upside down funnel. That's a good one to have in the notes. How about if I went like this? This idea would be a good thing to have in the notes. This has an asymptote on the y-axis itself. Where would this one have its asymptote scooted? Right, 2. So if I go with this, I get an asymptote at 2, because 2 is what make the bottom 0. And then I get the same shape as the 1 over x graph. I wouldn't have that exactly maybe in the notes or in your memory, but the concept of it. Like if I did 1 over x plus 4, where would you head? Left 4 for an asymptote. And then use the asymptote to just be your home base to mimic this shape. It's 1 over x at its heart, sort of. So we go here, there. Zip. If I did this, we'd still go left 4. But instead of going ups and downs, we'd go ups and ups. Because now the squared, this shape takes over for squaring, this shape takes over for regular. Does that make sense?
Would it still go left 4?
It would still go left. Yeah, because negative 4 would still make the bottom 0. That would still be the vertical axis. So back to the task at hand. Small dominant terms for 1 over x. This is a graph we just sort of talked about memorizing. I do all that stuff as dotted stuff because those are just guidelines. Those aren't, we're not going to really touch or cross those. That's just guidelines for us. And I'm going to put some little stars here because that's the graph we want to resemble when we get in tight. So when we got out to the extremes, we want to mimic the large dominant term. When we get in tight, we want to mimic the small dominant term. So if I'm trying to like mimic this for a while when we're at the end, and mimic this for a while when we're in the middle, I need to get from here to there while each one sort of follows its path for a smidge. I'm not supposed to cross anything. The way to accomplish that is to work just in this space. So sort of follow tight for a while, gradually get farther away and change my mind, and then gradually get tighter. There we go. If I want to try to get from here to here without crossing anything, I need to work this zone. I need to stay inside that space. So if I'm trying to get from here to here with each one following its pattern for a while, I'd follow this for a while, change my mind somewhere in the middle, and follow that one. Now, did my U-turn have to go through this specific point, or could I have a U-turn that goes through there as my own judgment call? I mean, maybe I should have U-turned there. Or maybe you would U-turn a little deeper. Like, where you make the U-turn is a little bit of a toss-up. But we're going to get something close to this, something close to that. We're stuck on the inside of all this dotty stuff, and we need to make a U-turn in the middle. You could graph that on your calculator and see if it looks like that. It should. It's sort of interesting to do a graph with no table, no derivatives, not even any points, right? Like, we did not find one ordered pair for that. We just kind of guesstimated the shapes because this graph is going to dominate when we get to the end. The other graph is going to dominate when we're in tights, and it's going to make a resemblance to what the real graph is, and it just sort of looks like that. If you wanted an actual, like, thing, if we plugged in 1 and 1 is 2 on top of 1, like, the point 2, 1 should be something, but whether that's there or not, I don't know. But it would, if we graph, let's graph it on the calculator and hope it resembles that. Now, would I send a man to the moon based on that? I would not. But if we just need like a sketch graph, that's not bad. Let's see how it goes. X squared plus 1 divide x. Whoops. Yeah, it goes in standard. And you should get something like this. It just disappears into the y-axis at a certain height. And then you get something that's coming like this, and that disappears into the y-axis also at a certain height, because it's supposed to. Like, we're supposed to be basically disappearing into those asymptotes as we rise. Do this just for fun. Graph in y2, y equals x, and hit graph. And you'll see that these two things just sort of blend into that. And if you graph y equals, let's go 1 over x instead in y2. If you graph y equals 1 over x in y2, you can see that it sort of blends in, you know, on those as well as blending into the asymptote. It's sort of like the two dominant term graphs got married and had a baby. It sort of resembles them both in different ways and completely doesn't resemble the other one in different ways at different times. That's what the dominant terms are about. And now maybe dominant term like makes sense. When you get big, it looks like the one graph. When you go little, it looks like the other graph.
I do have one question. How do you know when it goes in like one graph and not the other?
It just can't cross anything.
I'm saying like there's...
So if you're trying to get from here to here and not touch anything, you have to stay inside the line.
I'm saying like the opposite side, like the circle.
To get from here to here is an impossibility because you can't cross. Remember, there's an unshown asymptote because the y-axis is an asymptote. So getting from here to here is hopeless. Getting from here to here is hopeful as long as you live in that zone. You wouldn't cross any line.
So if the x-axis was the asymptote, would it be in the other, like, I don't know. Would it, instead of being in those two, like, sections, would it be in, like, the other ones?
That's what I was asking.
If that makes sense.
I don't...
So you know how it's like a quarter circle?
Yeah. If we had this were a thing to follow, it's possible we might have to, like, snake through there. I don't know if that's your question.
So it's like a quarter circle.
So I got A, B, C, and D are the things we're trying to connect. I'm trying to connect star to star to star to star if I can connect the stars by following the pre-established path.
Yeah. Okay.
Here, let me draw them. So I would never try to draw anything in here because there's no stars down here. I'm scanning for my stars, connecting star to star.
So how come we draw in here and here and not here?
Because I'm trying to connect from A to B. So to connect from A to B without touching anything, I've got to be in there. Because if I started off drawing out here and try to get to B, I've got to cross stuff. I'm not supposed to cross anything.
No, I get it.
Does that make sense?
Yeah.
We can't cross anything. So if I'm trying to get from here to here and not cross anything, I've got to like live in there. But there are graphs where your paths might be like, there's one that I think has a U shape, and then it has like a 1/x shape, and we're trying to get like from here to there, in which case you've got to like snake through there like that, because that's the only path from here to here to avoid touchies is like through that world.
Will we ever have one that's like actually impossible? Like where,
Maybe.
okay.
What we're graphing is, we're going to graph the threes. So 3, 6, 9, 12, we'll graph those. But we'll do the lists for all of these. I think there's 28 of them. So syllabus will go, I believe, 1 to 28. We'll graph the threes. Some of them start off like easy in the sense that the graph itself, let me do number 1. So they start off like artificially easy. So if I go to do number 1, horizontal, vertical, slant, large, small. So number 1, straight out of the horizontal. Zero. Vertical, 1. Slant,
Yes?
No.
no. Top isn't 1 higher than the bottom, and if we have horizontal, we can't have slant. To do the large dominant term, we'd have to try to divide, and on this it's bizarre. If you try to take the bottom into the top, that goes in 0 times, and the remainder would be everything is the remainder.
Okay. Okay.
So that sort of starts off weird. If you go to graph it, graphing would just be just graph itself. We just did a few of these a minute ago whenever we were memorizing shapes and putting things in our notes a second ago. This was creating a vertical asymptote at 1. And how does anything in the 1/x family go? Well, here and there. Just graph it, just flat out graph it. We don't have to try to blend the graphs together. We can just flat out graph that just based on the fact we memorized the 1/x. Horizontal asymptote of 0 sort of graphed itself because it is the x-axis. The x-axis is a horizontal line of 0. So we have that asymptote, we have that asymptote. I wouldn't worry about the large, small dominant terms on this one. I'd worry about it if this is graphable and this is graphable, then you blend the graphs together. But if one of those is a 0, just graph the other one and move on with your day. So it starts off, the first few start off a little bit easier than the ones that we were just doing. Does that make sense? And I guess tomorrow's probably just homework day, unless you have something you feel like we can accomplish in 4 minutes. Then you have something that's 4 minutes worth that would help you.